This lecture is an introduction to Logisim, which is the program that we will be using to simulate logic circuits. To follow along with this video, and to participate in our next several in-class activities, and to complete the next couple of homework projects, you will need to download Logisim. So you should do that right now. From the Logisim webpage, we can go to the Download section, and then follow the SourceForge link and select Download. We will be downloading a jar file, which you will need to have Java installed in order to run. And then if things are set up correctly, you should be able to double-click the jar to run Logisim. When we open Logisim, we get a canvas on which we can place and connect circuit elements. My plan for the rest of this video is to go through all of the circuits from the other video you watched on logic gate combinations. And for each of the circuits in this video, we're going to build that circuit in Logisim so that you can see how to use Logisim to build circuits out of gates and wires, and how to simulate the inputs and outputs of those circuits. We can start by building a circuit that contains a single NOT gate. The basic logic gates and or a NOT appear up here at the top left of the Logisim window. And so we can click on the NOT gate and place it onto our canvas. After we have placed our gate, Logisim automatically switches us to the Select tool, which we can use to select our gate, drag it around the canvas, and drag wires for the inputs and outputs of this gate. If we want to give this gate an input, we can select the Input Pin option and place that on our canvas, and then drag from the right-hand side of our input pin a wire that connects up with the NOT gate's input. We can also place an output pin on our canvas and connect the output wire from our NOT gate to the output pin. Most of the time in Logisim we'll be using the Select tool because that's how we connect wires, and that's how we select components of our circuit and move them around on the canvas. But sometimes we'll also use the Poke tool, which is the hand icon here. And if we select that, then for the input pins in our circuit, we can click them with the Poke tool to change their value. So when the input has a value of 1, that causes the output, since we sent that through a NOT gate, to have the value 0. Whereas if we give it the value 0, then the output of our NOT is 1. The other tool we have here at the top left of Logisim is the Text tool, which we can use to place labels on our circuit canvas. So we could label this as our NOT gate from the video. And then with the Select tool, we can move our text box around. And it's also noteworthy that when we have selected an element on the canvas with the Select tool, we get this pane on the left-hand side. That's a bit hard to see, but you can then, with the Select and Edit tool, change some of the properties of the circuit components. So for example here, I could change the font to be size 16 to make my label a little more visible. The next circuit from the video is an AND gate, and we also have AND gates as one of the built-in options at the top left for Logisim. So we can select an AND gate and place it on the canvas. Now this AND gate, if we hover over the left-hand side, has 5 different inputs. And if we want, as appears in the video, a 2-input AND gate, then we need to select our gate and modify its properties. In this case, the property that we want to modify is the number of inputs, and if I change that from 5 to 2, now my gate only has 2 pins on the input, and so we can drag a wire out from each of those inputs, and now we could connect those to pins or other elements of our circuit. Let's again add some input pins, and we'll add 2 of them and connect those to the 2 inputs of our AND gate. And then we can add an output pin and connect that to the output of our AND gate. And now, with the poke tool, we can verify that this AND gate has exactly the same truth table that's displayed in the video. When both of the inputs to the AND gate are 0, the output is 0, and that corresponds to the first row of the truth table. The next row of the truth table is input A is 0 and B is 1, and we can actually label the pins on our canvas to make clear which of these corresponds to A and B from the diagram. So with the select tool, I can choose one of these input pins, and then when I'm editing its properties, I can give it a label, and I can give it the label A, and now that appears on the circuit. And I can select this pin and its label and call it B. And now we can use the poke tool to change the inputs of our circuit to correspond to the next row of this truth table where A is 0 and B is 1. So I'll change the value of B, and we still get an output of 0. The next row of the truth table is when A is 1 and B is 0, so we can toggle both inputs. And again, we see that the output of the AND gate is still 0. Whereas if both inputs are 1, the AND gate should output a 1, which we can confirm with the poke tool. We'll add another label to our canvas. The next example is an OR gate, so we can add one of those to our circuit. And again, it has 5 inputs, so we want to change the number of inputs to 2, and we want to give it input pins. I can use Control-C and Control-V to copy components of the circuit, so that's a quick way to get another input pin. And I can connect these up to the inputs of the OR gate, and I can copy and paste the output pin, drag it to where I need it, and connect it to the gate. And once again with the poke tool, we can confirm that this truth table matches the video. When both inputs are 0, we get an output of 0 from the OR gate. If the first input is a 1, we get a 1. Same with the second input. And if both inputs are 1, we still get an output of 1. And this matches the truth table from the video. The next circuit combines multiple gates, and it starts with an OR gate and then negates the output of the OR. So let's go back to Logisim and pick the select tool, and now we can highlight our OR circuit, and with all of those components selected, we can Control-C, Control-V, and drag our copy to a new location. And now we can select the wire connecting our OR gate to the output and delete with the delete key, move the output out of the way, and drop in a NOT gate. Now if we connect the output of the OR gate to the input of the NOT, and the output of the NOT to our output pin, we get a circuit for a negated OR, or NOR. And the negation of OR is 1 when both inputs are 0, and it's 0 for all of the other combinations of inputs, which corresponds to the truth table from the video. The video talks about the intermediate value on the circuit C, which corresponds to this wire on our circuit, and you can tell the value of C from the color of this wire. The dark green corresponds to that wire carrying a low voltage, which means a value of 0, or the bright green, like we see now, means that that wire is carrying a high voltage, which means a value of 1. Up next, the video builds a negation of an AND, so we can copy our AND circuit, bring it down here, and disconnect the output pin by deleting a wire. And now we can drop in a NOT gate, which will connect to the output of our AND and connect its output to the output pin. And now with the poke tool, we can verify that when both inputs are 0, the NOT AND outputs 1. If one of the inputs, A, or the input B is 1, we're still outputting a 1. But if both inputs are 1, we output a 0. And that corresponds to the truth table from the video. Next, the video builds a circuit that is, by De Morgan's law, equivalent to NOT AND. If De Morgan's law is not a term that you have heard before, then you might want to watch the extra video I linked on Boolean algebra. And instead of building a new circuit, I want to add this as an extension to our NOT AND circuit so that we can use the poke tool to verify the equivalence of these two circuits. I want to use these same input pins as input to the components I'm adding now. I can hover over an existing wire and click and drag to branch that wire so that this same value will be the input to another logic gate. Here we want a NOT gate, and we'll connect up this wire, and we'll add another NOT gate and make a branching wire from input B. And now we want an OR gate, and since I already have some OR gates that are 2 inputs instead of 5 inputs, I'll copy and paste one of those and drag it over to my circuit here and connect up the wires. And now we'll add an additional output pin, which we connect to the output of the OR. And so we see that this circuit is equivalent to the one from the video, but since it's connected to the same input pins as our NOT AND, we can cycle through the possible input values and verify that these two versions of the circuit each produce the same output for all possible inputs. For 1, 1, they both produce 0. 1, 0, they both produce 1. 0, 0, they both produce 1. And 0, 1, they both produce 1. And so these two circuits are equivalent, as we would expect by De Morgan's law. Likewise, the next circuit should be equivalent to NOT OR, and we can demonstrate that in the same manner. So for all possible combinations of input, we get the same result from these two outputs, which corresponds to the truth table for this circuit being the same as the one we saw before for NOT OR. I've now made some room on the canvas so that we can work through some additional circuits. This one has 3 inputs, A, B, and C. And I can label them appropriately in the left-hand pane. And this circuit ORs B and C, and then ANDs the result of that OR with A. And now we could use the poke tool to verify each of the rows of the truth table. The first row should have an output of 0, then 0, then 0, then 0, then 0, and then the last 3 rows should be 1s. And when the video gets there, we see this result of the first 5 rows are all 0s and the last 3 are 1s. Next, the video switches around the location of these AND and OR gates, so I'll make a copy of my circuit. And if I were to try and drag this OR gate to the position of the AND, we see that the wires try to come along for the ride. Logisim likes to keep components connected if it can. And so if I wanted to replace these components, I could do Control X and Control V. And now I have a disconnected OR gate, and Control X, Control V, I have a disconnected AND gate. And now if I drag this into position here, it connects to those wires, and I can drag the OR into position and connect to these wires. And so if we go through the inputs in order this time, when all 3 are 0, we get an output of 0. Likewise, when only C or only B are 1. But then once B and C are both 1, or for any of the possibilities in the bottom half of the table, we get a 1. And so returning to the video, we see the corresponding truth table of the top 3 rows are 0, and all of the rest have an output of 1. For this circuit, I'm going to start by copying my input pins. And I'll also copy the output. And now we want 2 AND gates and an OR. And we want to connect the outputs of the ANDs to the input of the OR. And the output of the OR to the output pin. So we should have 5 zeros followed by 3 1s in the truth table. And the video reaches the same conclusion. Note that this means that this circuit is equivalent to the top one, and that makes sense because these 2 circuits correspond to the 2 sides of one of the distributive properties of Boolean algebra. For this next circuit, I'll start by copying most of my AND. And then we want an additional AND gate plus a NOT gate. And the NOT gets its input from B, and then gets combined into the final AND gate. And then we'll connect up an output pin. And here, if we go through the truth table, we get 0, 0, 0, 0. And so this Boolean circuit is outputting the constant value 0, which we would call a contradiction in Boolean algebra. Our next circuit has 4 inputs. And now we want to AND A and B, AND C and D, and then OR the results. And now if we wanted to, we could go through all 16 possible input combinations to fill in the truth table, or we could reason through it a bit more systematically. For this circuit to output 1, the OR needs to output a 1. And for the OR to output a 1, we need one or both of the inputs to that OR to be 1. And so to get one or both of the inputs to be 1, we need it to be the case that either A and B are both 1, or C and D are both 1, or all four of them are 1. So we could set A and B to 1, and that will make the output 1, regardless of how we change C and D. Or we could set C and D to 1, and that will make the output 1, regardless of how we change A and B. Let's once again give ourselves some more space to work with, and then build this circuit. We'll start with inputs A and B. And then we want 2 NOT gates, 2 AND gates, and an OR. Now we send NOT A into the top AND, and NOT B into the bottom AND. And we send A into the bottom AND, and B into the top AND. And then we OR together the outputs of those 2 ANDs to get the output for our circuit. And we can cycle through our possibilities to fill in the truth table. If A and B are 0, we get 0. 1, 1, 0, which agrees with the video and corresponds to an exclusive OR gate. As the video shows, exclusive OR is common enough to have its own gate symbol, and there is an exclusive OR gate, as well as many other gates built into Logisim. Over here on the left-hand side, we have many more menus where under gates, we can find all of the basic options like NOT and an OR, as well as many more options, including an XOR gate. Like the and OR, the default XOR gate has 5 inputs, so we can change its number of input pins to 2, and then we can connect up our A and B from the previous circuit, and then give this an output pin. And now if we try to cycle through the possible values, we see a common issue with Logisim, which is that I have accidentally made a connection that I didn't want to make. We have crossed the wires for A and B at the input to this NOT gate, which we can see if I were to drag the NOT gate aside. This dot here indicates that those 2 wires intersected, and if those wires are carrying different values, then our circuit has a nonsensical input. And so I can fix this with my NOT gate moved out of the way. I can delete the offending wire and reconnect. And now the wire from A is passing under the wire from B, and we don't have the unwanted intersection. So now we can go through the possible inputs to this circuit, and for all possible combinations, we see that this circuit outputs the same thing as our XOR gate. In our in-class activity, we'll see how to build other logic gates out of the basic AND, OR, and NOT components, and we'll get a chance to analyze the behavior of many more logic circuits.